Hi, I'm Alistair Donaldson and I'm a lecturer in the Department of Computing at Imperial College London, and this is the third and final in a series of lectures I'm recording about GPU Verify, the technique and tool being developed at Imperial as part of the CARP project for analysing GPU kernels. In this lecture, I'm going to go into details of some subtleties associated with reasoning about barriers. Then I'm going to tell you how the techniques from lecture 2 can be extended to handle conditional code and loops. And finally, I'm going to talk a little bit about how GPU Verify tries to automatically infer invariance for loops using the Houdini algorithm. So the first thing I'm going to talk about is semantics for the barrier operation. So in CUDA, a barrier is represented using the sync threads function, but in the slides I'm showing you here, I'm just going to talk about barriers to be consistent. So what the CUDA documentation says is that barrier waits until all threads in the group have reached this point, and all global memory accesses made by these threads prior to barrier are visible to all threads in the group. So this is the natural interpretation of barrier. But then it goes on to say that barrier is allowed in conditional code only if the conditional evaluates identically across the entire thread group. And this is a little bit more subtle. And in particular, it goes on to say otherwise the code execution is likely to hang or produce unintended side effects. I mean, I think it really just, the rule here is that behavior is undefined if this condition is not satisfied. But what does this condition really mean? Well, I would say that my interpretation of this paragraph would mean that this kernel is obviously bad. So we've got a kernel called foo, and this is using OpenCL syntax rather than CUDA syntax. If a thread's ID is 0, then we have a barrier. Otherwise, we have a different barrier. So if the rule is that threads have to get to syntactically the same barrier, then this isn't going to happen in this kernel. Thread 0 is going to get to the first barrier. All other threads are going to get to the second barrier. And then thread 0 will be stuck waiting for the other threads to reach its barrier, which they never will. And likewise, threads 1, 2, 3, etc. will be stuck waiting for thread 0 to get to their barrier, which it's not going to do. So the kernel, you would expect it to deadlock. And this rule of barriers being syntactic objects, so that threads must reach the same syntactic barrier, is the intention in both OpenCL and CUDA. So this kernel is obviously bad. But what about the following kernel? So this is a contrived example, but when you're building a verification tool, you need to really understand the semantics of operations, and often you think about weird corner cases to try to see whether you've got your semantics right. So consider this example. We have an int x, and we set x to 4 if our ID is 0. Otherwise, we set x to 1. Okay, so for thread 0, x will become 4. For threads 1, 2, 3, etc., x will become 1. Then we have an int y, and thread 0 sets y to 1, and threads 1, 2, 3, etc. set y to 4. Okay, so they do the opposite things with x and y, thread 0 and the other threads. Then we have a loop that loops with a loop counter I. I ranges between 0 and x. So for thread 0, I is going to be ranging between 0 and 4. For threads 1, 2, and 3, it's going to be ranging between 0 and 1. And then we have an inner loop with a loop counter j. And j is going to range between 0 and y. So for thread 0, j ranges between 0 and 1. For the other threads, between 0 and 4. So clearly, every thread is going to reach whatever statement is inside the inner loop 4 times. They're just going to do it in different ways. In particular, thread 0 is going to do it by executing an outer loop iteration with a single inner loop iteration, then another outer loop iteration with a single loop iteration, etc., 4 times. Whereas the other threads are going to execute one outer loop iteration in which they're going to do 4 inner loop iterations, and then they're going to leave the loop. Okay. So the question is it okay to have a barrier as the statement inside this loop? Is it all right for a thread to reach the barrier having done an iteration of the outer loop while other threads have done an iteration of the inner loop? And if you read the CUDA documentation, this sounds like it should be okay. However, if you code up a kernel based on this example, but where you do some things to some arrays, you find on NVIDIA hardware you get very strange results, and it's clearly not okay. Now, the OpenCL specification is a little bit more precise. It says that if barrier is inside a conditional statement, then all threads must enter the conditional if any thread enters the conditional statement. That's similar to what CUDA says. But it goes on to say that if barrier is inside a loop, all threads must execute the barrier for each iteration of the loop before any are allowed to continue execution beyond the barrier. Now, I think this is in somewhat ambiguous English, but I think it goes some way towards explaining that the example I showed you on the previous slide is not okay. The reason it's not okay is that the inner loop is going to be executed many times by threads 1, 2, 3, but only once by thread 0, so they're not going to synchronize on the barrier having done the same number of iterations. But I still don't think it's crystal clear from the description here. So what we do with GPU verify is check for barrier divergence, where threads would hit different barriers or hit the same barrier but under different numbers of loop iterations. We check this efficiently and naturally using lockstep predicated execution. And this is also a nice way for us to handle conditional code and loops. And I'm going to explain how lockstep predicated execution works. So what we do for the purposes of verification is we model all threads executing the kernel as if they were executing in lockstep. Now, this isn't completely coincidental with the fact that on NVIDIA and AMD hardware, threads do execute to some degree in lockstep. In fact, we got the idea by being inspired by the way the hardware works. But actually, our use of lockstep execution is independent of the fact that these GPUs do use lockstep execution. So the idea of lockstep execution is that at every step of execution, every thread executes precisely the same instruction. Now, this is fine for straight line code, but for conditional code, it poses a problem because different threads might take different branches in a conditional. So the way we deal with this is we simulate the conditional code using predicated execution. So it's easiest to see how predicated execution works by considering a simple example. Suppose we've got something like if E, then do S1, otherwise do S2. When threads execute this statement, what we're actually going to do is first we're going to introduce a Boolean variable P and have all threads evaluate E into this Boolean variable P. So E is a thread local expression, so it may evaluate differently for different threads. So different threads may get different values for P. Then we use this funny notation, P implies S1, to mean every thread executes this statement, and if P holds, the thread does what S1 dictates. Otherwise, the thread actually no-ops. So all threads execute S1, but those threads for whom E is false are disabled during this execution. And then we do the opposite. So all those threads for whom P didn't hold are enabled while executing S2. But crucially, all threads execute this statement. It's just that some of them executed in a disabled state. So we've transformed this conditional code into a piece of straight line code. So the conditional code has been eliminated. And this is an idea that's actually used a lot in optimizing compilers. It's been around for a long time, and we're using it in this novel context of GPU kernel verification. Loops are a little bit more tricky to handle. Suppose we've got a loop while condition E holds, do statement S. Now, it may be that E will evaluate differently for different threads so that some threads may leave the loop before others leave the loop. I mean, it might be that you have an expression E such as thread ID is less than N, okay? And that is going to be different for thread 0 and thread 1 depending upon what N is. So the way this is handled is all threads evaluate the loop guard, E, into a predicate P. And then the threads all continue to loop while P holds for some thread. So as long as there is a thread still enabled for the loop, all threads continue to execute the loop body. And now the loop body is guarded by the predicate P. So we change the statement S into P implies S to mean that S has no effect if P doesn't hold. So if a thread really should have left the loop, then the execution of that statement S has no effect for that thread. And then P is updated. So if P holds, a thread updates P to be the current value of the loop condition. And this is important because the statement S could have modified variables occurring in E, probably has modified variables occurring in E if the loop is to terminate. So this forces all threads to continue execution of the loop until every thread is done with the loop. So inserting predicates in this way ensures that at any point of execution, there is a current predicate guarding execution of a statement. So this predicate determines which threads are enabled and which threads are disabled. And this gives us a nice way to check for barrier divergence. So when a barrier is executed and the predicate of execution is P, then we need P to be uniform across all the threads. If P is non-uniform, so if P holds for some threads and doesn't hold for other threads, then this either means that the threads have diverged on conditionals, they've gone into different conditional parts of a statement, or it means that threads are executing a loop in a non-uniform way. And in the example I showed you a few slides ago, this would correspond, for instance, to thread 0 having finished the inner loop and ready to do the outer loop again, while threads 1, 2, 3 is still doing the inner loop. In fact, with our predicated semantics, all threads would continue around the inner loop, but now thread 0's predicate would be false. Threads 1, 2, and 3's predicates would be true, so we would say that the predicate is not uniform. So we require either all threads to be enabled when we execute a barrier, or all threads to be disabled. But if there's disagreement about enabledness, then execution aborts because we have barrier divergence. So let me show you now how we can translate statements with a predicate. So suppose at any point of execution we have some predicate P, and this translation scheme shows how we will translate a statement into a predicated form where the statement is predicated by some expression P. And initially, at the top level of the program, P would be the expression true to say that there's no constraint on execution, all threads are enabled. So suppose we have an assignment, x becomes equal to e. What we want to do is update x to the value of e if the predicate P holds, otherwise leave x alone. And this is easy to encode using a ternary operator. So we have two threads that we're modeling, and for the first thread, x1, we say that if the predicate holds for thread 1, for the first thread, then we assign e with respect to the first thread, so e$1 into variable x. Otherwise, we just reassign x into x. So this has the effect of being a no-op. And we do the same thing for thread 2. So basically, x becomes equal to, if the predicate holds, then e, otherwise x. If we have a read from the shared state, x becomes equal to a of e, then what we do is we call log read and check read as before. However, now we call these procedures with a predicate stating whether the thread is enabled. So in the case of log read, because thread 1 is the logger, we pass in p1 as the predicate, and thread 2 is the checker for check read, we pass p2 as the predicate. And I'll show you in a few slides' time how we use the predicates in the implementation of log read and check read. And then we havoc the receiving variable x as before, except that if a thread is not enabled, the thread hasn't really read into x, so we should leave x alone. So what we do is the following. We say x becomes equal to, if the predicate holds, then star, meaning choose an arbitrary value for x, otherwise give x its old value. So this is like a conditional havoc. We're havocing x only if p holds, otherwise we're leaving x alone. And now writing is handled similarly, so log write and check write are called, but this time they have a predicate parameter, p1 in the case of log write, p2 in the case of check write. So this is assuming we have some predicate, but where do the predicates come from? Well, they come from conditional code. So suppose we have if e, then s, otherwise t. The way we translate this is we have an incoming predicate p, and what we're going to do is we're going to compute a predicate q by strengthening p with the conditional test e. So we say for thread 1 that q1 becomes whatever p1 is and the result of evaluating e1. So if the incoming predicate was false, q is guaranteed to also be false because the thread can't become enabled if it's already disabled. But if the incoming parameter is true, if the incoming predicate is true, then q gets whatever e evaluates to. And then we also evaluate the negation of e, strengthened with p, into a fresh predicate variable r. So r becomes equal to, if the incoming predicate holds, r becomes equal to the conjunction of the incoming predicate and the negation of the expression e. So now each thread has q and r. Okay, they may both be false, but they can't both be true. And then we translate the then side of the conditional with respect to the predicate q, and we translate the else side of the conditional with respect to the predicate r. So this is quite a natural predication scheme. The predication scheme for loops is a little bit more complicated. First of all, every thread evaluates the loop guard e into a predicate q strengthened with the incoming predicate p. So q becomes equal to the conjunction of the incoming predicate and the loop guard. And then we say we keep looping while at least one of the threads is enabled. So if both the threads are disabled, if q doesn't hold for both threads, then we leave the loop. Okay? But if q holds for at least one of the threads, we keep executing the loop body. And what we do is we translate the loop body s with respect to the predicate q, and we then update q to be its old value and the new value of the loop guard. And this means that if the loop guard becomes false, q will become false, and if that happens to both threads, we will leave the loop. So if we have a sequence of statements s and t, then we just translate them each. And now with a barrier, we replace a regular call to a barrier with a call to barrier that takes two predicates as arguments. And I'll show you how we implement barrier in a minute, but essentially we're going to check that these predicates agree. If they're both true, that's fine. If they're both false, that's fine. But if they're different, we have barrier divergence and we abort. So now I just need to show you how we implement these log read, check read, log write, check write procedures with predicates. So log read now takes a Boolean enabled. If enabled is false, then log read is being called for a thread that is disabled, meaning the thread is not really executing the read, in which case we definitely shouldn't log the read because the thread hasn't actually done a read. So if enabled is false, we simply exit this procedure. If enabled is true, then we do the trick I showed in the last lecture of non-deterministically choosing whether or not we want to log this read. So this is exactly the same as before, but the whole thing is guarded by enabled. So enabled records whether the first thread is enabled. If it's not enabled, we do nothing. Okay? And log write is similar. And then check write, it also takes an enabled argument saying whether thread 2 is enabled. If thread 2 is not enabled, then there's no need to check whether this write caused a race because the write hasn't really happened because that thread was disabled. So we have an assertion, which is as before, but we say that the thread must be enabled for there to be a problem. So if the thread is enabled and thread 1 logged a write, then the write offset is not the same as the offset coming in here. There's a small typo in this slide. This off should really be offset. Okay, and we do a similar check for the case of a write-read race. So enabled records whether the second thread is enabled, and if the second thread is not enabled, there's nothing to check because the second thread is not really here. And check read is similar. And then barrier is implemented very similar to as before. What we do is we first assert that the enabled parameters agree. So enabled 1 says whether thread 1 is enabled, enabled 2 says whether thread 2 is enabled. If they're both enabled, that's fine. If they're both disabled, that's fine. But if one's enabled and the other's disabled, that's not fine. That means that they've reached different barriers, or they've reached the same barrier having done different numbers of loop iterations, which is illegal. Okay. And then, if the first thread is disabled, in which case, if we reach this point, the second thread must also be disabled. We return from the procedure because we're not really executing the barrier. The threads have not actually reached the barrier. Otherwise, we do what we did before. We assume that no reads and no writes have occurred. And we do this for every array. So this is how barrier is realized with predicated execution. Okay, so now we have a procedure for taking a kernel with loops and conditionals. And by the way, I've shown you this for structured programs with ifs and whiles, but actually we have a technique that we published at the ESOC 2013 conference showing how this can be realized for arbitrary reducible control flow graphs, which is a bit more complicated, but it's at some level the same techniques are going on. And we can take this kernel and transform it into a sequential program that models the execution of 2 threads using predicated execution to handle loops and conditionals. And I would like to verify this sequential program. If the kernel contained loops, the sequential program will contain loops, and for verification to work, we need to find loop invariants. We're going to use Boogie to do verification, and Boogie is a verification system where loops are abstracted using invariants, and generally invariants need to be provided either by the user or by some tool. So Boogie has some facilities for generating invariants, but invariant generation is a very hard problem, and it's usually best solved using a domain-specific invariant generator. So because loop invariants are very difficult to write by hand and we would like to infer them, we've been looking at using Houdini, which is an algorithm proposed in 2001 by Flanagan and Leno as part of the ESC Java project. And we've been looking at using Houdini to infer invariants automatically where possible. So what I'm going to do now is I'm going to leave the presentation and show you a little demo of how invariants can be used to aid in the verification of kernels and try and explain, give some intuition for how they can be inferred automatically and how Houdini works. So now to illustrate how loop invariants work in practice, I'm going to go back to the reduction example that I showed you in the first lecture. And just as a sanity check, I'm going to check that GPU verify can still verify this. So I think we had block dim equals 1024, grid dim equals 1, kernel.cu. So GPU verify is actually inferring an invariant for the for loop in this example in order to prove race freedom. And in this case, it manages to do this relatively quickly. We can turn off invariant inference by saying no infer. And this tells GPU verify, don't try to infer a loop invariant, just try to prove the kernel directly or using user-supplied invariants, which I'll show you in just a minute. And now GPU verify won't manage to prove the kernel race free because it does actually need an invariant to prove this kernel. And it's given a whole bunch of possible data races. So if we think about this, it's important to know that d is a power of 2 when analysing this loop. If d is not a power of 2, then this algorithm doesn't work. So it's been designed for d to be a power of 2. But d is modified in the loop, so without an invariant, we don't actually know that d is a power of 2 during the loop. So we can supply manually an invariant about d being a power of 2. We have this macro is power 2, so we can use it for d. Okay? We can say invariant is power 2d. We place an invariant right before the guard of a loop, and we use C's comma operator to separate the invariant from the loop guard. An invariant is a keyword we've added to the GPU Verify front end to allow users to specify invariants, which generally we don't want them to do because we want to infer these things automatically, but it's a feature for expert users and also for the development team in trying to work out how to verify something so that we can improve our invariant inference. So now if I try to verify this kernel, actually this invariant is not a true invariant. So the tool is reporting various races. I'm going up here and I think it will, yeah, there's a message here saying that the loop invariant might not be maintained by the loop for some thread, and it's this invariant that d is a power of 2. And the problem here is that actually d is going to be a power of 2 until the loop exit, at which point d will be 0, which is not a power of 2. So for this to work, we actually need to consider the case where d is 0. So we can change this to be is power 2 or 0, and if I change the macro to be called is power 2 or 0, and I remove the condition that x is non-zero, so now I'm just saying that x is a power of 2 or 0, and I rerun verification. Let's see what happens. So now this was not enough to prove race freedom of the kernel, but if we scroll up, we don't see a problem related to that invariant. So it's managed to prove that invariant, but that invariant isn't enough to prove race freedom. And the reason is that in this loop, there are reads and writes from and to the array A, and once we translate this into a boogie program with these instrumentation variables, those variables will be part of the modifies set for the loop. So at the loop head, the verifier has to consider that those variables could have arbitrary values. There could be a read or a write to or from A anywhere, and those may well race with the accesses to A occurring inside the loop. However, if we look at the kernel, we can see on loop entry there will be no reads or writes because there's nothing preceding the loop. Furthermore, the loop doesn't have any breaks or continues, and the last thing that happens in the loop is a barrier, sync threads. So there can't be any reads or writes at the head of the loop. But without inference, GPU Verify doesn't know this, so GPU Verify would infer this, but we've told it not to. So we have to say here, invariant not write A. So we're telling GPU Verify that there are no writes to the array A at the loop head. So now, if we run the tool, I don't think it will manage to verify it, but it should have fewer errors. Okay, so it's given fewer errors, and the problem is that we also need to tell it that there are no reads from A. And now it should verify all being well. Okay, so this is an example of providing invariants manually by hand. So GPU Verify's job is to try to guess loop invariants automatically for the program text. And what we want to do is to have a scheme where GPU Verify can make rather liberal guesses. It can guess all kinds of possible invariants and have a way to converge on a subset of these invariants that is an inductive invariant to prove race freedom of the kernel, so that it can discard invariants that turn out to be wrong. We don't want it to have to guess exact invariants, because then if it guesses them wrongly, verification will fail because of those invariants, not because of the data races. Okay? So we use the Houdini algorithm to do this. And the way Houdini works is that somehow a pool of candidate invariants is constructed, either by a user or from a tool. And Houdini, the Houdini algorithm says, first of all, let us try taking the conjunction of all these candidates as a loop invariant and seeing whether that verifies the program. And it usually won't verify the program either because some candidate won't hold on loop entry or because some candidate is not maintained by the loop. So Houdini involves running a theorem prover to see whether things work. And if the invariants don't work, then you can remove some bad candidates and keep going, okay, and keep running the procedure so that you gradually remove bad candidates until either you eliminate all the invariants and fail to prove the program, or you find a subset of the invariants that is inductive and allows you to prove the property that you care about. So what I want to do here is demonstrate how Houdini would be used to verify this example. So what we actually do with GPU Verify, in this example, we don't need to know anything about the range of the powers of 2 in question. But GPU Verify doesn't know that, and for many kernels it's important not just to know that a variable is a power of 2, but to also know that it's a power of 2 in some range. So whenever GPU Verify sees something that makes it think a variable might be a power of 2, in particular a variable being right shifted or left shifted or multiplied by 2 or divided by 2, it generates power of 2 candidates for that variable. So what this involves doing is generating a candidate invariant, and I've provided a feature where the user can specify a candidate invariant manually. I've now made these invariants candidate invariants, but GPU Verify would also generate a bunch more candidate invariants. Often it's important to know that a variable is a power of 2 or 0. Sometimes it's important to know that it's a power of 2 and is not 0, or that it really is a power of 2. So we might have a candidate that d is not equal to 0. Okay? And now we might want to know that the variable d is bounded, so we can actually generate a candidate saying that d is less than 2 to the power 0. Okay, so it's less than 1. I'm going to define a little macro up here. Power 2x is going to be defined as 1 left shifted by x. So we might want to know that d is less than 1, or that d is less than 2, or that d is less than 4, 8, 16, 32, etc. And GPU Verify generates all of these candidates, and I think it stops at 2 to the power 16. So I will add these all here. Okay, so we're saying that we think d might be a power of 2 or 0. We think it might not be 0. We think it might be less than 1. We think it might be less than 2. We think it might be less than 4. We think it might be less than 8, etc. And we also think it might be the case that a write has not occurred and that a read has not occurred at this point. All right? And we could chuck in anything we want here. For example, we might have some fault in our invariant generation algorithm. We might generate some stupid invariant like the invariant false, for instance. It might be that false is an invariant for the loop, which obviously can't be true. But I want to illustrate to you that it doesn't matter if we have these kinds of invariants, because these are just candidate invariants, and if they're wrong, they will be discarded by the Houdini algorithm. So now, assuming I've not made any syntax errors, which is quite possible here, I can run GPU Verify again. This time I will turn inference on, and I'm going to pass an option to Boogie, the trace option, to tell Boogie to tell us what it's doing, and also I'll run GPU Verify in verbose mode so that that information is passed to the console. Now, unfortunately, I can't tell GPU Verify to take our candidates from run Houdini and not generate its own. It's not configured to do that. So it's going to generate all of its candidates, which in fact overlap with some of ours, and it's going to take the candidates I've specified manually, and then it will run Houdini. Okay, but I just want to show you the output, and then I will explain it. So if I run this, it's running the various stages of GPU Verify, and now it's running lots of little verifications. So I'll let it finish and then I'll explain the output. Okay, so if I scroll up here, what it's done is it's verified the reduction function. This is the mangled name of the reduction function. It took 0.2 seconds to work out that with the current set of invariants, this function was not correct. And it's kicked out the candidate invariant, which is called B16. Now the B's are actually candidates that are generated by the tool, and the C's are candidates generated by the user. So we can go down and have a look. It's kicking out a bunch of the invariants it generated, and then it starts to kick out some of the invariants we gave it. So it kicked out, for example, the invariant C2. It found that C2 was not true. It found that C3 was not true, that C4 was not true, etc. So what are these invariants? Well, what I'm going to do now is I'm going to rerun GPU Verify with another option called keep temps. And this causes the tool to keep the various intermediate files it generates while running. So I'll run it again, you should see exactly the same output. And if you remember, it kicked out the candidate C2. So now if I open up, in fact I can open it here, I can say xf kernel.bpl. This is the Boogie program that GPU Verify actually produces to be verified. And as part of the Boogie program, there are a bunch of Boolean constants which are marked existential true. And this is a way of saying that Houdini should use these constants to toggle candidate invariance on and off. So for example, there's a Boolean C2, which is used to toggle user-supplied invariant number 2. So let's have a look for that in the code. Let's have a look for C2 being used in the Boogie code. So here, there is an assertion. So this assertion has a lot of tags associated with it. We say assert, and then there are a bunch of attributes which we can ignore. So you can ignore the stuff I'm highlighting here. We assert that if C2 holds, then what this says in bit vector notation is that D must be less than 1. Okay? So if C2 holds, D must be less than 1. So if you imagine that C2 is set to false, then this assertion vacuously holds, because false implies anything. So if C2 is set to false, it's as if we didn't have this assertion. If C2 is set to true, then the assertion is true if and only if the right-hand side of the implication holds. So if C2 is set to true, it's like we have got the right-hand side of the implication. If C2 is false, it's like we switched off this assertion completely. And this assertion says that D is less than 1. So going back to the kernel, if I could use Emacs, kernel.cu, this is this candidate here, it's this one, D is less than 2 to the power 0, i.e. 1. And this is clearly not true, because we can see that D starts as n over 2, which is going to be a large value. Okay, so D is not going to be it's not going to be invariantly less than 1. But GPUVerify doesn't try to do some fragile analysis and actually work out what the loop bound is. It could do, but the analysis would be fragile. Instead, it does a more brute force but robust thing of trying a very wide range of prefix closed ranges of powers of 2s and gradually working out whether this lies in some prefix closed range. It involves kicking out a lot of these candidates. So you can see that we had to kick out C2, then C3, then C4, then C5, then C6, etc. up to C11, okay? And if we go back to the Boogie program, let's have a look at what C11 is. So C11 says that D is less than 512, okay? What about C12? What does that say? C12 says that D is less than 1024, all right? Well, if you look here, when we invoked the kernel, we said that there were 1024 threads. And now going back to the kernel code, we've said that D is initialized to the number of threads divided by 2. So D will be less than 1024. So that candidate wasn't kicked out, that candidate held. So the idea of this Houdini-based approach to inference, which I should stress is not a new thing. Houdini's been around for a long time. It's a very cool technique, but we are using it in a new way in GPUVerify, is that you have some means for generating lots of candidate invariants, and then Houdini takes care of deciding on a subset that is an inductive invariant, and then it checks whether that inductive invariant is good enough to prove race freedom of the program. So if I remove all these candidate invariants, get the program back to its original form, and now I run GPUVerify, you will see with the trace option, it doesn't talk about our C variables because they were for the user-supplied candidate invariants, but it is kicking out B16, B15, B14, B13, etc., B12. And that's because it is actually speculating invariants similar to the ones I showed you manually in analyzing this kernel. Okay, so to summarize, I've shown you the problem GPUVerify tries to solve. I've shown you the tool in action and some examples and given you a flavor for how things work under the hood. Things are a lot more hairy under the hood than I showed you because I showed you like nice structured program examples, but the tool works generally on the intermediate representation generated by the Clang compiler. So if you look at the programs GPUVerify generates, they're much less nice looking than the examples I showed you, but I hope I've given you a flavor of how things work. So I've missed out quite a lot. I haven't given you full details of invariant inference. In fact, I showed you inferring invariants about variables being powers of 2. That's very simple to infer. We have more complicated invariants for working out the access patterns of arrays, for example. I showed you that we can tolerate certain kinds of benign data races using an example, but I haven't shown you how this actually works in the tool, which involves extending the instrumentation of logging and checking. And the details of the translation into Boogie, especially the way we handle pointers, is quite intricate. It took some time to get right. And actually, a summer student, Igor Kaistomov, spent a long time working on implementing decent error reporting for GPU Verify. This is something which I think made a difference from the tool being something I could explain on slides and then give a rather useless demo of, to something where I can give quite a nice demo because you can see the tool reporting nice messages. Earlier, it used to just give you a trace through the Boogie program that was generated, not a trace through the OpenCL kernel or CUDA kernel. So having someone work on that was really very useful. And I think it's difficult to kind of something that's quite difficult to publish, and therefore people don't tend to spend time on it. But I think no one is going to use the tool unless it provides some kind of decent feedback to the user. So I think it's worth the effort. And there's a lot of ongoing and future work in this area that we're planning to pursue in the research group. In particular, we're looking right now at richer shared state abstractions. We're looking at something called barrier invariance for proving properties that can't be proven if we abstract the shared state completely. We're looking at supporting atomic operations, and yeah, we've got some initial ideas about how to do that. The tool doesn't currently treat atomic operations properly. And at the moment, we're just looking at analyzing GPU kernels. But what we would like to do in future is look at analyzing whole applications. So a C++ application, which invokes multiple GPU kernels to perform some task and check that this whole thing is race-free or divergence-free. Or maybe look at stronger properties like functional correctness properties. Although we've deliberately steered clear of functional correctness because we want to do something simpler, race freedom, and do it really well and try and make it as automatic as possible so that people will use it in practice as part of their day-to-day development. So please go and check out the GPU Verify website to learn more about the technique and tool. And do get in touch with us if you would like to have any assistance in getting set up with the tool. It's available under Windows, Linux, and we have it working on a Mac, which we haven't made available yet, but we can help you do that if you want to get it running on a Mac. And if you'd like to get involved contributing to the project, then yeah, we'd be very keen to talk to you. Thanks for your attention.